welcome to another Digital Dimensions CADcast. I'll be your host, Joseph Richter, and today we're going to talk about SOLIDWORKS equations made easy. And on the agenda today, I'm going to talk about the setup for equations, things to keep in mind when you're creating your part file. Then I'll walk us through a simple equation, such as this dimension is equal to that. Then I'll carefully describe global variables versus link values, when to use one over the other. Then I'll take you through an example of a more complex equation. Then I'll describe how to export an equation to a text file so you can reuse it in another part file. And then I'll show you the if-then statement that we can use to control dimensions and/or features. And now the main question, what exactly are equations? Well, here I describe them as the tools of the trade for capturing and maintaining our design intent in our part models. Well, put simply, equations are the way in which we can capture and maintain relationships between our dimensions. For example, this dimension will be equal to that dimension plus 5, or this dimension is equal to that dimension plus another dimension. So we have the ability to set a relationship between our dimensions with equations. Okay, so to set up for an equation, one of the first things that you want to think about when you're creating your model is renaming your dimensions. So renaming your dimensions, you can go to the Modify dialog and swipe over the name that they give you, which is typically D1, D2, etc., and go ahead and name it. Now, the reason you'd want to rename your dimensions is so that it's easier to generate your equations when you're writing them, because then you'll understand which variables you're calling on when making your equations. The other things that we may want to do is show the dimension names. That way we can tell which dimensions have already been given a name. And then finally, after we've extruded our cube here, we may want to see all of our dimensions, those from the sketch as well as from the features, so we can show those dimensions as well. And our first example, as I mentioned here, will be a cube, and the design intent for the cube are all the edges will be equal. And the equations that we will generate here will be height is equal to length and depth is equal to length. And for the first example here, I mentioned that we're going to generate a cube. And in order to draw a cube, I'm going to start off with drawing a rectangle. And on this rectangle, I'm going to add a few dimensions. Now, when you're generating your dimension, you can give it a name. So I got height, and then I'll generate length. Now, in order to see the names of the dimensions that I've generated, you can go to the View drop-down and specify dimension names. And now I can see my height and my length. In order to create our first equation, when you double-click on a dimension, you can type in an equal and then specify the dimension to be equal to. So here I'm going to say that the height is equal to the length. This height dimension now has the sigma symbol next to it, indicating that it's being driven by an equation. I can see that by double clicking on it, and I can see height is equal to length at sketch 1. And when we exit the sketch to proceed with the extrude, new to SOLIDWORKS 2013, we can actually type in an equal now in our dialog boxes, and then I can click on the dimension to be equal to. In order to see all of the dimensions on our model, you can go to the Annotations folder, right-click, and show Feature Dimensions. So now I can see height is equal to length, and this D1 is equal to length as well. In fact, I'm going to go ahead and rename this. We can also take a look at our equations by right-clicking on the Equations folder in the tree and specifying Manage Equations. This shows me that the height is equal to length at sketch 1 and the width is equal to the length at sketch 1. Now, setting up an equation like this, we know that the parent of this entire model is length at sketch 1, which means if I change this length dimension and then rebuild, it's going to update the other two dimensions. So again, the primary objective of writing an equation is to establish a relationship between our dimensions to maintain our design intent. So in our cube example, I created two direct equations. One, height is equal to length, and the width was equal to length. Well, in doing this, this created a parent-child relationship. In other words, I cannot change either child, either the height or the width. I must directly address or change the parent, the length. This can make it awkward for making changes on a part file, in which case sometimes it's desirable to avoid this relationship. So I want to point out that there are two other ways to accomplish this equal relationship without causing or creating a parent-child relationship. The two methods are global variables and linked values, also known as shared values. And also, new to SOLIDWORKS 2013, I want to mention that they gave us the ability to add equations into any dialog box during a feature edit. And as described, the way that we set up this model, we have captured parent-child relationships. The 75 here is the parent, the children are width and height. Now, what does this mean? Well, if I double-click on the width, I cannot change the width because it's being driven by the parent, the length. Likewise, on the height, I have no ability to change the height without modifying the length, in which case when I adjust the parent, both children update. Now, in this example, I have only one place to modify the model. This may create confusion when others go to modify my cube. So, in a lot of cases, it is desirable to minimize these parent-child relationships if possible. So, what I'd like to do is go ahead and delete some of these equations and try another approach. I'm going to go ahead and modify my initial sketch and eliminate one of my dimensions. Anytime when generating a sketch, it's always desirable to capture a geometric relationship between my sketch entities instead of adding extra dimensions. So in this case, I've added an equal between my sketch entities. At this point, I can go to my length dimension, double-click on it, and say that this is equal to a text tag of cube. And you'll notice when I start typing in a variable, SOLIDWORKS gives me the option to create what they call a global variable. This global variable will essentially be a text tag assigned to the value of, in this case, 75. So now I can see the sigma symbol indicating that the length is equal to the global variable of cube. When I exit my sketch, I can go to my width dimension, double-click on it, and say that it is equal to my global variable cube. From there, even though both of these dimensions have an equation driving them, I can change the global variable from either place, thereby minimizing the parent-child complexity of relationships when people go to modify this cube. The other thing I'd like to point out about global variables is the fact that they show up underneath the equations folder right here. The other way to have generated a global variable would be to go into Manage Equations and type in a new global variable here. These global variables again show up under the equations folder and is actually a best practice in SOLIDWORKS for driving dimensions on parts that are important to the overall design. Now, if you're going to require multiple configurations of your part, there's another method that I'd like you to consider. So I'm going to go ahead and eliminate these global variables. And instead talk about link values. When you right-click on a dimension, you can specify link values. Link values are a special type of global variable that will rename the dimension. So as I give this the name of cubed linked value, it renames the dimension based on the link value name, and then I can link the other dimension, right click, link value, and then specify from the drop down cube link value. From this point I can now configure that dimension and specify multiple configurations. And now we have multiple versions of the cube. While global variables can be controlled in a design table, I would say a majority of users are using the configure feature, configure dimension functionality, and for that reason I recommend linked values. And my next example that I want to share with you is that of a right triangle. My design intent here is I want to prove out Pythagorean's theorem. In other words, I want to maintain a 90-degree corner, a right triangle, when I change the length of either side A or side B. So to set this up, I'm going to add the global variables of A, B, and C, and I'm going to write the equation a squared plus b squared is equal to c squared. Or rather, to solve just for c, I'm going to take the square root of a squared plus b squared. Okay, so in this example we'll write a more complex equation. So to get started, I'll draw in a triangle. And with this triangle I want to add some dimensions because we're going to prove out Pythagorean's theorem. And while I'm at it, I'm going to add some global variables of A and B. As well as an angle to prove whether or not we have a right triangle. At this point, I'm going to go ahead and manage the equations, and we'll say that C is actually going to be equal to the square root of A squared plus B squared. And when I hit OK, it looks like A squared plus B squared equals C squared, and we have 90 degrees for our angle. And then when I modify this, I let it rebuild and it adjusts. So it doesn't really matter which one I modify, it looks weird until I hit OK for it to update. But we can see that it is calculating Pythagorean's theorem and maintaining 90 degrees. So you can see if this was my design intent on my model, once I've established these relationships, the system takes care of the rest by calculating the answer for the variables. Again, we mentioned that you can rename these dimensions. So like this 40, we said that was A. This 40 was B. And this 56 was C. Again, that would probably be a fundamental difference between link values and global variables, is the fact that global variables do not rename the dimension, but link values do. Once you've generated an equation and it works really well, you can export it to a text file. This will allow you to basically take that text file and import it on a similar part model. Now, this will work so long as the dimensions are named the same, including the sketches. In other words, if you're in the habit of renaming your sketches, they do need to be named the same. Okay, as mentioned, if you wanted to save an equation out to a text file, all you need to do is go to Manage Your Equations and Export. When you go to Export, you go ahead and save it out as a text file. It asks me which items to save out and whether or not to keep them linked to that text file. Because I've saved it out and maintained its link to the text file, I can now no longer change the model from here. It's been locked directly to that text file. I'm going to go ahead and open that text file. And now from this text file you can see my global variable of A is equal to 40. The sketch dimension A at sketch 1 is equal to the global variable of A. I can see global variable of B is equal to 40. The dimension B at sketch 1 is equal to the global variable of B. And we can see that the global variable of c is the square root of a to the power of 2 plus b to the power of 2. And then finally, the dimension c at sketch 1 is equal to c. In order to reuse this, when I go to create a new file, I'll generate a new sketch and a new triangle. The key to making this work is that the dimensions are named the same. So I'm going to name this dimension A, this dimension B, and this dimension C. From there, I'm going to go ahead and turn on my dimension names again from the View drop-down so I can see ABC. Now when I go to Tools, Equations, you'll notice that I have no global variables and no equations. But I can import from my text file and I will not link it to the file. So now it fills out my global variables and adds the relationship between all of my dimensions to those global variables, and then I simply rebuild. And then I suppose I would add a dimension to verify that it's 90 degrees. And just like before, I can modify these and watch it update. Now, had I chosen to keep it linked to the file, then I could only modify these dimensions from that text file. Okay, so let's show that again. I'm going to drop in yet another triangle. And then throw in my dimensions. Maybe the angle. And then go to Tools, Equations, and import that text file. This time around I will link to the file and then rebuild. Because it's linked to the file, I have no ability to change it. Okay, but again I can turn on my dimension names to see what's going on here. Now if I were to save this, I could close it and then modify that text file. So maybe I made A 60 and B I want to make 75. I save that file, and then when I go to open, I rebuild it, and my sketch has been updated. 60 and 75. While maintaining the right triangle. Keeping in mind this equation could be shared across multiple files, maintaining these global variables. And the next example that I'd like to share with you is an Allen head wrench. As I described equations as the tools for maintaining design intent, I figured I'd go with that theme, and hence we have an Allen head wrench here. Now the design intent for my Allen head wrench will be the following. I want the length to be 10 times the hex dimension. I want the handle to be half of the length, and I want to use an if-then statement to control the radius or the bend from the length to the handle. So I want the radius to be 20 if my hex size is under 20, otherwise it needs to be 30. So in my picture example here, my hex is 25, therefore my radius is 30. Alright, and in this example we'll explore some more ways to use equations to control how our part changes. So just like before, I'm going to go ahead and show my feature dimensions as well as display my dimension names. Again, when adding your dimensions, you want to give them names. That way when you're writing an equation, this will all make sense. As discussed, our design intent, we want the length to be 10 times our hex dimension. Our hex is going to be this 15 down here. I'm going to go ahead and assign it a length value because I want to configure this part. And we said we want the length to be 10 times the hex. So just like before, double click on your dimension, type in equals, pick your parent or driving variable times some constant rate of change, and then hit OK. That way when my hex changes to say 20, when I rebuild, the length becomes 200. I'm going to leave it at 15. For our next design intent, we want the handle to be half of the length. So handle, that's our child, should be equal to the length divided by 2. When I hit equal, that updates. So again, I go back to the hex, make that 20. When I hit rebuild, this length becomes 200. The handle should then become 100. So let me zoom out to see that, and you can see that again my dimensions are responding to change. I'm going to flip back to 15. And finally, the last design intent here is we wanted the radius to be 20 if our hex size is under 20, otherwise I want it to be 30. So that requires that we use an if-then statement. In order to do that, when you double click on your dimension, we're going to say that that is equal to if our hex dimension is less than 20, then our radius value will be 20, otherwise it's 30. So that means as long as this hex is below 20, then the radius will remain 20, but once it's over 20, say like 21, then my radius becomes 30. So we can apply if-then statements to respond to change as well. So let me manage equations to show that. The radius is equal to if hex is less than 20, then the value is 20, otherwise the default value is 30. So if hex less than 20 is true, then it's 20 millimeters. If that's false, then it's 30 millimeters. And then to configure this file, again you can right click on 21, the hex dimension, and configure it and give it some sizes. So configuration of 10, hex of 10, configuration of 15, hex of 15, configuration 17, hex of 17, 19, 19, 21, 21, etc. Okay. And I should be able to go to my configurations and verify that every configuration rebuilds and these rules respond to change. And for my last example that I want to share with you is again another tool. I hope this CADcast has provided you the tools by which to capture and maintain design intent between your dimensions. So here with my last example is a combination wrench. The design intent for the combination wrench is as follows. The hex dimension should drive the design. The diameter of the ends should be twice the hex dimension size. The length of the handle should be 10 times the hex size, and the fillet that I have on the open end should be suppressed if the hex dimension is less than 12. And finally, I will choose to use link values in order to configure this part without a design table. And for our final example here, this model has a lot more features than the last, and I'm going to go ahead and roll through here. The reason this model has more features is I am going to want to configure it, and I would illustrate that as I roll through here, I'm renaming my features, which again is a best practice. Along with each feature, I'm renaming the dimensions as needed. Here on my engraving, you'll even see that I've linked the size to the name of my configuration. Okay, so when I go to add additional sizes, my size will update. So here I've got a hex cut, and I create a hex cut on the opposite end. I make a 12-point hex cut, which is another hexagon simply rotated. So if I wanted a 6-point and a 12-point version, I can do that simply by turning off one of my features. And then finally I finish the part off with a fillet on the end. Okay, so just like before, I want to go ahead and show my feature dimensions. okay, as well as turn on my dimension names. Because I want all of these hexes to be the same size, these 14s, as a rule, I want to apply a link value. So I will right click link value. Again, I'm generating a link value simply because I want to configure this without a design table. My next design intent for this combination wrench is I want the end to be 2 times my hex, and then I want the length to be equal to 10 times the hex. And then perhaps I want the head depth to be twice the thickness of the midsection. And finally, I want to use an if-then statement on this fillet here. So for example, when my hex gets below 12, I want that fillet to be suppressed. So in order to use an if-then statement with a feature, we simply go into the equations dialog box and we go to features, add that feature, and I want to say that's equal to if my hex is less than 12, then I want it to be suppressed, otherwise unsuppressed. And from there we'll go ahead and add our configurations. So we'll right click, configure dimension, and we'll do a 10, a 12, 14, 16, and 18. And I'll go ahead and turn off my dimensions. So right click annotations, show feature dimensions, and then simply scroll through these sizes, and we'll see that this fillet gets suppressed with number 10 because the hex is less than 12. So SOLIDWORKS equations, size 10, you can see that updated. Number 12, you can see size 12 updated. 14, etc. If I show those feature dimensions, you can see that that hex is in fact updating. I turned off all the dimensions so you could see the model update. But here you go. So here you can see that adding equations between your dimensions will allow you to capture relationships between those dimensions for greater design intent and control of your models. Thanks again for joining me on another DDI CADcast. I'm your host, Joseph Richter. To find more tech tips and CADcasts, please visit us at ddicad.com.